Okay, welcome to the lecture 8 session 1. Uh, I'm all of you who are here. I'm going to talk something related to whatever we have done in the last class, and we are going to see one more topic that called the constant satisfaction thing. And in the previous class, we were talking about the serial search, and before that, we were talking about whenever a problem, a machine learning problem, a artificial intelligence problem is given to you, how you can solve that problem. So one approach that you know that all these are the possibilities, and you somehow try to find out the solution where there is a solution. So for example, into the game of chess, what is the solution? Something that is a winning position, that when you win, and then you want to find out what is the move, what are the moves that are going to take you that particular step, and then you are going to just go ahead with the first of. So let's get started. So in the last class, we were discussing these things that in the continuous state space. So I was talking about that whenever you want to solve a problem, there are states. And what do I mean by the state? So let's assume that it's a game of chess. Okay, it's a game of chess. So all the board position are the states. Then you connect them. One can be connected with another by just having a edge and say that if you go for a particular move, you would be reaching to this particular state. These are discrete because states are discrete, but sometimes you be into such scenarios where space is continuous. What is a continuous space means? Space. Let's assume that you are standing at some field, and now you are allowed to go in any direction. Then would you go ahead? The problem is if you want to find out the best way to go forward, it is going to be very difficult because the general understanding is this, that initially you go ahead till end until you find out the solution, and you forward one step into that particular direction. Okay, understand this? The ways that you find out from here, this is the solution, and then in that direction you move one path. But to this, you have to find out all the possible places which are there. You have to evaluate all the possible places where you can move. But into the continuous space, there is an infinite number of possibilities. Do you understand why it is an infinite number of possibilities? The question, sir, before starting, can you please point out what sort of question could be asked in mid-semester examination? So it we will talk about into the end. Okay. So my question is that do you understand that why many possibilities into the continuous space? Because if you say that you are standing at some particular location, let's assume that you are into this particular position, so you can go in x direction, minus x direction, y direction, and minus y direction. But if these are the roads, generally this is the scenario, that this is a discrete way to going somewhere. This way also you can go anywhere. But if I allow you that you are here and you can move into any direction, so in how many ways you can go? You can take 0 degree move, 1 degree move, 2 degree moves. How many degrees moves is possible? 360 moves. And between 0 and 1 degree, again you can say that a lot of possibilities are there. So therefore, going precisely in a particular direction in the hope of the solution is going to very difficult, because earlier what our system was, that whenever you are here, you are evaluating all the possible places, and in case what are all the possible places? 4 options, and then wherever you go there, so you again explore the 4 possibilities, again 4 possibility, and try to build tree, and at the end you find out there is some place that is a goal place. Then say that okay, this is the way to go to the goal, and therefore I am going to go into this particular direction. Space, what is going to happen? Since you start building the tree, there are how many branches? Infinite number of branches. So they're just exploring all of them is not possible, because it's going to take the infinite amount of time. So therefore it becomes a difficult problem. So what is go around? How can you tackle this problem, the problem is to use gradient. What is it? Gradient is the slope. Gradient is the slope. You try to see that in all directions, in all the directions, you see that what is the gradient into x direction, what is the gradient into y direction, and then this you would be able to find out the vector that would tell that this is a particular direction where the slope is highest. Means you are getting at this particular moment highest amount of advancement if you go into that particular direction. So you can use this gradient to move into particular direction. You are into the non-deterministic scenarios. In the non-deterministic scenarios, what happens that sometimes you don't know that what is going to happen. Okay, if a state you take this action, this should happen, but sometimes it may not happen. For example, you are here into the Pilani. If you want to go to the Delhi, you sit into the car. It is expected that your car would take you to the Delhi, but sometimes what happens in between there is some problem. You have to come back, able to reach. This might also be possible. Something else can happen. You can reach some other place. So if you consider those things to happen, this scenario is a non-deterministic scenario. We had an example where we had a vacuum cleaner that when it is asked to do a suck operation, then it also cleans the nearby rooms. So therefore, we are thinking that we are going to this particular state when take this action, but it may be possible that you may reach to other states because other possibilities are also there. So in those scenarios, we have seen that in the non-deterministic places, you have to go for the AND OR search, and this is a very important point. I just want to tell you once again that what is the AND OR search. Okay, what is the AND OR search? Let's assume that you are here, and there are three possibilities that you can take. So you take this particular action. So sometime if you take this action, it may be possible that you reach to the two, not a single state. Here, if you may reaching, if you are into the state Q1, you may reach state Q2, state Q3, and sometime you may reach Q3 and Q4. Why Q3 and Q4 I am writing? Because it's such an environment where you cannot very confidently say that what is my status. So therefore, yeah, I'm thinking that you may be reaching into the state of Q3 and Q4. So for if you take another action over here, so if you take some action onto Q3, you may be reaching to you take some action, so maybe reaching to another state. But if you take that same action onto the Q4, you may be reaching some other states. So what's required that where you are into this state and you take this particular action, you take action so that you move into this direction, and here more than one states are there. So in this line, in both the trees, you need to find out some state that is a goal state, and you're not going to stop. In other places, all the routes should be followed, but AND places, this is a R point and this is AND. This is the question where all the branches you should traverse and find out a solution for them. And or you can choose one of them and go ahead. In the last class is the deterministic action. And sometimes the third thing that we have seen in the last class is the partial observation states, where when percepts are not sufficient to pin down the exact state, means you are not knowing that what is my state. You don't know that what is my state, what would happen. What action you are going to take. This is a big question. So therefore, you try to build up a belief. It means you do some action and you say that after taking this action, I am definitely going to be into this particular state, and from that state I would take this action, and then I will be able to solve this particular problem. So to see this, what is the partial observations? In the partial observation, what is going to happen? That you are not able to localize that what is your state. What is your state? What action you can take? This is a big question. But it turns out that in some scenarios, you can develop a concept of the belief state. That my belief is that I would be into belief state is actually a superset of the states where various states would be there into one chunk. You can say either I am into this state or this state, and overall this is going to the scenario, and then taking this action would lead you to the other belief step, and using this belief state transition, you may be able to reach to the final goal state. This particular thing that sometimes the environment is unknown. You don't know that what is the environment, and you are just left behind to find out the solution. Then two things you need to do. First, you have to find out that what is the environment. To understand the environment, you have to take the action and then see that what are the percept you're getting. By this, you are localizing yourself and building the model of the environment, and then one by one solving the particular problem. So therefore, this is a very important part. On search and enroll environment is very important thing where you interleave, means you first take the action, see what is the output, and creation and action you are mixing them so that at the end you discover that what is there, and then you build the model, and then you can find out the solution. We then in the last class we came to the adversarial search. That is also a very important thing. Adversarial search happens in the case of games. For example, let's assume that you are playing a game of chess. What would happen? You are having a turn, and then the opponent is going to have a turn. Your task is there are two players into the game. There are two players. One is min, he is the opponent, and another is max. You are the max person. Okay. So every time you want to find out something, what you want to find out? Win that you want to find out. So we assign +1 to the win, and +1 to the lose, because +1 -1 should be equal to somebody is winning, somebody is losing. So overall summation should become 0. So we plus the win. The minus is the lose, or not -1. 0 is the lose. Plus 0 is the lose. +1 is the when you win. 0 when you lose, and half when you go for the draw. Let's say this is a kind of scenario you have. So that the summation is always 1. Where all the time you are getting distributed at the same. Okay. If you are half and half, therefore 1. If it's in, somebody get 1, somebody get 0. Therefore, you got overall summation that you need to distribute is 1. So other person is opponent is getting 1 and you are getting 0. Again, it is 1. So there are two peoples who are one you who is max, and person is called the minimum. So whenever you go for a turn, you advance your move. So you want to maximize that profit, because for board position you have there, you want to maximize the profit. So you are increasing the value, and minimizing means the second person, when his turn comes, he want to minimize that value so that you don't get that much money. So he would try to minimize that value. So we have seen that to completely define this thing, we need to define some of the things that we assume that the environment is deterministic, fully observable. Turn taking means there is a turn, I'm taking a turn, then you are taking turn. Two thing, zero sum summation is going to be constant. Initial state is a 0. Initially there is some initial board position. It is you call this function player S. It means that it would that who's in this particular state, in a yes state, whose charge is this. So player S would return either min or max. He can take any action when, if you see that if you have a board position, you ask from the function players, you would tell whose turn it is. That he can take any action from the actions. How? Because every time you cannot take the same action. Huh? In different state, different actions are available. So all this function action says, it would tell that these actions are possible. So one of the actions the player can take. So which he have to take is a bigger question. So somehow he would figure out that this is the action I'm going to take. When he takes this particular action, whatever action he want to take, then he gets some results. Okay. If the test, then he would be his state is going to change. If his next state is a terminal state, means it's very possible the game has off. Then whatever reward is there, utility specifies that what is the reward, and he gives the reward. Otherwise, you can't do the game. So I think I've completed this. Then I would take a question that is a very important. Okay, so you understand that they get the he gave a word that is utility of that particular state. Max must find a contingent strategy. This is a very important thing. Max should have a strategy, not be a single point. If I'm into this state, what action should I should take? This would not work. He should also have a strategy that if in this state I'm this action, then he is going to take this action, then I'm going to take this action. So he should plan accordingly. He should have a strategy, big plan. Then he can win into the game. Now, in between, before going to the next point, I want to take action that is very important. Many of the students are asking that there's a question into the quiz that were asking that which of these things have the partially observable environment. Okay, so two options were there: automatic vehicle and the path picking robot. So there are two other options: game of Go and I think one more option. So people were confident that at those places the environment is fully observable. But there was a confusion between the vehicle car driving and the second is part picking robot. We discussed in the class that there was a slide where we have discussed that part picking robot can be a partial observable environment, because if you have only one camera, if you have put it based on that your robot is navigating, so he may be seeing only partial things, and therefore it could be a partial observable state. So you can think yourself that if you have only why it is needed to have only this, why you only needed to restrict yourself. Most of the time, only seeing partial thing you can solve the problem. Therefore, people are using part picking boat as a partially observable environment, because you know that even if you are partially observing the thing, but by using the partial observation also you can solve the problem. We have seen this here also. Sometimes see this partial observation, when you have partial observation, sometimes going through the belief states you can solve the problem. So the thing is here, so if you part picking robot is there, you solve the problem. So part observation is fine, because using the partial observation you can solve the thing. So for the answer in the slide it was written that the part picking robot is a partial observable status. But point is that can you make it fully observable? Answer is yes, because you can implement more answers, so that because it's a environment where the things is there and your robot is going to pick the thing, so you can put more cameras, and therefore this partially observable states could be fully observable, but it is not required. Therefore people are not putting. Point is they can make it fully observable, and that have not going to improve the performance. Therefore people are not doing, but it's possible. But second option, automatic vehicle car driving, observable. That is no, because everything is changing. What things are there in front of you? You cannot put a camera in everywhere, so that on all the earth, wherever there is a position, you see that things are available. Every time the things are changing. People, when the person is going somewhere, he can take in any turn. There could be environmental conditions. So many things could be there. Okay, so things could be there. So it becomes quite impossible, because it's not a lab environment, it's an actual environment where domestic vehicle car is driving. You cannot apply the things to find out, take it fully observable. That's why in terms of, you can compare both of things, and you can say that okay, automatic vehicle car is more partially observable than the another. Therefore, the right answer is this. This particular question was put just to find out just to give you more thinking about this, because you should not be just lucky ka fakir, just seeing the question and you are applying the answer. You should be too independent thinker. You should to apply your brain. Sometimes you should be able to apply your brain and tell, no, this is a partial observable state, but under certain condition we can make it fully observable. But this particular thing we cannot make it fully observable. For the question was framed like this, so you can think, you can apply your brain. I think you can understand. You can understand. If you have any question, please ask. Once again, final line. Let me tell you this: the thing that parking robot works in the environment. And fully observability is not required, because with the partial observability we can achieve a full accuracy. Because using belief steps, this particular example is there in front of you, that using the belief step, it may be possible that using half the information, partially observable environment, we can solve this particular problem. So therefore, don't make it the fully observable. The point is, be a lab environment, we can make it fully observable. That is for sure important. But if you want to make fully observable the vehicle, you cannot do it, because there is a car. What is inside your car currently, you cannot put. Inside the crust, you cannot say, because you are going to fly over something, say tsunami comes, something, whatever happens, a road got broken in front of you, everything could be happening. So you cannot make all that kind of things so that it becomes fully observable. It is not possible. It is impossible. This is fundamental. The question written to you just to let you this kind of thinking. Okay. So is it clear now, Markandeya? Okay, for asking this question, many of the students are asking. So that okay. Thank you much. So let us go forward. So seen these things in the last class, that how we can formally define all these things, and we have seen this thing in the last class also. The half move is a one play. One play means let's assume A is you, and then you have three kind of moves possible: A1, A2, A3. You took, so let's say you took A2. Then he have something. He would also take. He also have three kind of possibilities: C1, C2, C3. The opponent may take C2, and then from coming here to here, actually makes one progress into the game. Now the point is that you are the max and he is the min. How you are going to decide over the, how you are going to decide that what should be my appropriate next turn, what should I take? The point is, you would consider, when you are here, you would consider that what your opponent would do, then you can go. That's why I am asking that out of these things, you would not see that which is the most beneficial to me. You would to see that what is the policy, what is, after taking this particular action, what the opponent is going to do. So here you see that in the case of B, you see, let's assume that the opponent has the three choices, and in the choices he can take me position where I can get the advantage. I get utility of 3, utility of 12, and utility of 8, means the profit of 8, 12, and 3. So definitely we would choose this particular path, B1, because it would give him, it would put me into the position where I can only advance to the 3. This is can do for me. Similarly, if I take this particular action, he will be into the scenario where he can take the action from 2, 4, and 6. Definitely, opponent would go for the action C1, so that I would be into the situation 2. So therefore, minimum is 2. So here minimum is 3. Here minimum is 2. So if I take the action A3, the minimum is going to be 2. So what should be my strategy? I know that if I take this particular option A3, then he would take this particular turn. I would be into the scenario to get into 3 only, 2 only. So best one is to take the action. Which action? Can you tell me which action I should take? Which action I should take? I should take B. I should move to B by taking the action A1. Okay, right. So I should take the action A1 to reach over here. So by this I can maximize my chances. Given the game tree, optimal strategy can be determined from the minimum value of each node, and this is how it is evaluated. I think this is not a big thing. You initially, if you want to find out that what max action I should take, so you see that if it is a terminal test, you need not to take any action. You see that if you are whatever state you are, if it is a terminal test, means if it is a final test, then you see whatever is available to you. You cannot play this game. But if you are max, then you should find out the for all actions. You want to find out what is the minimum thing that is available with your opponent, and you should take that minimum out of time mistake. It will be arg max. Okay, I'm sorry, I have written the max. It should be arg max. So let me just note it down. There is typing mistake. it should be min-max, it should be argmax. Okay, the argmax function, I think we have discussed earlier. Someday we have discussed this, na? Someday we have done argmax. So you know the argmax function, or should I explain? Just tell me. Argmax function. Yes, I know. Okay. So you want to find out that particular action that has a maximum value for this thing, and this value you are taking min across all the trees. So therefore, of all these minimums, you want to see that which particular action gives me the maximum, and you're taking this. Similarly, this is the argmin, and you are going to perform this particular option. Okay, if you are minimized, then you would be taking the something that is okay. Okay. So action average is the optimal choice that we have seen, the algorithm that we have seen in the last class. Recursive procedure, recursion proceed all the way down to the leaves. Time complexity is b to the power n. What is the b to the power n? What is the time complexity? How much time it needs to find out the solution? You will find out that what is the next move. To do this move, you have to go from top to down until you find out something that this is a winning scenario, and then in that path you see that what is the maximum, and then you take one path. This is going to be a big number because B, what is B? B is the branching factor. If you are here, how many other branches are there? You have to evaluate all of them. Then you go down and evaluate all of them until you reach to the particular solution. Let's assume the solution is there at the depth M, so it is going to take the order of M thing. Very big number. Okay. The seen that I think this part we have not seen. The number of nodes to examine the minimax search is exponential in the depth of the tree that we know. Sometimes, the very important option, sometimes we can make it b to n by 2 by using alpha beta pruning. So what is alpha beta pruning is a new thing that we are going to discuss. Okay, when applied to standard minimax tree, it returns the same move as max, but prunes the branches that cannot possibly influence the decision. So what happens sometimes in this particular tree, you have to explore all the places. Only few places exploration is sufficient to find out the best move. And you can find out this particular thing into the best way, then the time taken is going to be order of b to the power n by 2. That is a very big thing because ultimately what is b to the power n by 2? No, what is b to the power n by 2? B to the power m by 2 looks like under root of b to the power m. Okay, so earlier the equation was b to the power n. You compare these two equations, this equation with this equation, it says that only this part, since this part is same, you can take the inner part and you can compare root b with the b. Okay, root b is a branching factor. Earlier your branching factor was b, but this time your branching factor is under root b. So that is a big thing because every step you are using very less number of things. Okay, so we are going to do, we would discuss this into detail. So let's see this particular example. Okay, consider consider the two evaluated successors of the node C, X and Y. So this is what. Let me take it here. Okay. So what we want to discuss, we want to discuss this, that given this particular tree, okay, this is given to us. How can we find out? Let's say that we are into this scenario. Don't what these numbers are. Just view that we want to find out at this point what we want to find out. Find out what action we should take. What is the min max value? Okay, we want to find out min max. We want to find out minimax of root. Okay, So what it would be? It would be maximum value. It will be maximum value across all the three streets. Okay. So you take a maximum of initially you see three values are there, 3, 12 and 8. Okay. And second from this place. Okay. And so you take the minimum of this particular thing. Okay, that 2. Let's assume that it is x is y, min of n of y. Okay, and here you want to take the minimum 4, 5 and 2. Okay. So can you tell me that what is going to happen? That what is the minimum? What is the minimum from this place? Minimum from this place is 3. What is from this place? I don't know, but I know that this value, whatever value this ZB, Z is always less than or equal to 2. I know. Pardon me. If I take minimum from this particular place, this is going to give me some value always less than or equal to 2. Are you with me? From the third thing, I14, I see the value 2. Okay. So please write yes if you understand this with me. Yes. Look, what I want. Okay, I got yes. One yes, but I need one more yes. Mark and can you write yes? Are you with me? No. So I have to find out the minimum value for this root. So this is my objective is to find out the minimum value at the root. So this is the formula. This is nothing magical. We know that this is the formula. This is the formula that we have. Minimum of these values, because these values are shown to me, is going to be 3. Then you know. Minimum of these values, since values are shown to me, is going to be 2. And minimum of these value, I don't know the value of x and y, but I know that whatever value is this, it is less than 2. Hence, I want to find out the minimum. I am sure that minimum, because this value. Okay. Now, since the outer part is find out the maximum value. Okay, inside we want to find out minimum, outer part we want to find out maximum out of this. So what is the maximum that you are going to get? Can you tell me? Compare 2 and 3, you would say that I would pick this particular number. I would not pick 2. Third number, do you third number? The value of this thing is 2. Maximum value could be 2 only. It cannot. You only need to consider if there is a possibility that Z would go above the 3, because you want to maximize this thing at the outer place. It is maximization. You know that the value of Z cannot be greater than 3. It is because by construction it is less than 2. Because this equation it is only going to be less than 3. So therefore 2. So therefore you need to find out to explore the value of Z. Give single value. If the single value is given to you, you need not to explore further, and you can tell that value is going to be 3 to me. And fine. Okay. So same thing. Min of root is a minimization of this thing, and therefore you find out that this value is 3. What it mean? It means that whenever you find out this kind of scenario, you don't explore this particular part. Are you able to get this particular point? That you are into the scenario when you need not to explore all the streets. So this is what the basic concept is. So I have a question. Okay. Me? Do you know what I'm telling? I mean that in this scenario, you need not to explore this thing, and this is not a difficult scenario. Most of the time it would be, because time you would be able to see that going down is not going to be beneficial. Okay. So like these values are there, they actually try to fit these values so that it gets indication. This is alpha beta values. So, L beta pruning can be applied to the trees of any depth, and it is often possible to prune the entire subtree rather than just a level. So when you see that you need not to go ahead, so you actually pruned means prune is cutting. You have cut these place, so you don't go inside, find out the right solution. So only considering these parts would be sufficient. Okay, M is some node. M is better than n for the player. Then we would never go to the n in the play. If this is better, so we will not go to this part. So therefore, this part can be removed. So there is two values that we are going to use. Alpha is the value of best choice, highest found so far for the max. So alpha is the best choice, best value that we have, and beta is the value of best choice, lowest for the min. Alpha is the best choice for max, and beta is the best choice for min. Okay, for the max, what is the best? It is alpha. For the min, what is the best is the beta. In these two value, we can find out. How we can find out? This is the algorithm, and we would not go into it. I would just go to this algorithm by an example. I have put an extra point over here. Particular algorithm to just explain this particular points. Okay, let's see that how the things are happening over here. Okay, so this is once again the same example, and let me just put it here to tell you that what is happening over here. Okay, so initially how you start, look how you start. So let's assume that this is algorithm. What is the best that alpha can do? Alpha and beta is minus infinite. Beta is so you okay. Alpha. Okay. So you are going to find out which is the best way out of these three possibilities. You come over here. You put infinite 3 because see whenever you explore this particular tree, you wrote that 3 is the worst thing that you can do. Okay, because he can get the infinite profit. I think I should repeat this. Okay. Okay. This is the best that you can do. So he that 3 is the something that he can take. Then the actually got explored. Now it is got 12, but this particular node would not update this particular place because he knows that in the mix 3. So why should I go for the 12? Because it would be beneficial for the A. Thing is explored and out 8 over here. Then the same line, this also going to be neglected because means 3 possible. Therefore, B would go for the 3. But all the things are now explored. So C is that this is the best thing that I can do. So he put over here, and 3 sends that for this particular person, he tells that this is the best that you can get if you choose this particular thing. Out of all possibilities, what is best is written over here. Okay, so out of all the possibilities, 3 is the best that he can do. Then he would evaluate that what is here. He come down here, he evaluate the first one and sees that the value is 2. So this value, because for this node the 2 is the value available for him, he communicate to him that okay, you can take this particular way where the profit is 2, but it's not updated because why should he update it? Because he have the path for 3. Why would update this path to go to this particular place? It's not expanded. Then the next part sees that okay, no, I'm not interested, and he knows that since this particular node has explored something that is of the cost 2, have a better path. This is the point where he decides that I'm not interested in anything. Because whatever you find out is not interesting to me. So even if you are exploring anything extra, that would be given to me because now he has something to go ahead with the 2. So this particular adversary would go with the option 2. So these things are not evaluated because even if they are profitable to this particular guy, but it would not be taken as an R. So therefore these things are actually negated. Now these things are actually not explored, and we go to the another place and try to see that what is the best. Now we got this 14. a very good thing because you got 14. So he is very excited that okay, I got 14, therefore I can take not go to this particular place, go to this particular site because I got something 14. He's interested. Okay, chalo explore karo, explore to the next one. He then goes to explore the next one and surprisingly find out 5. This is a bad thing because D now, earlier the D has option of 14, but now D has one option, that is a 5. So D would not go for this particular option. He would cancel this option and he would check that I would take this particular route. See, this guy is also upset. Earlier he has places 14, now it puts 5. Okay, chalo is raste mein, on this way I got the 5. But again he wrote this thing and find out okay, this is 2 and this is actually the biggest problem, because now he got the 2. So for this particular guy has another way to go ahead with the 2, and if he take, and since he would not go with the 5 now this time because he have explored another path that is of the 2, he would take the path of the 2. Here it is 2, similarly it is sent to this place also, but this wouldn't be this particular thing because 2 is not useful because he has the path for the 3. So you can already think that if there are other trees available, so those trees would also be pruned at a particular moment when you find out that there is a possibility of 2. So this algorithm, so hope you understand, it's very algorithm. So you see this particular thing. So here one thing is very important to note, that if you have since you have explored this thing into this way, if here at this particular moment, if you come here and here at this particular place, if you instead of exploring 14, 5 and 2, if you have explored it 5 and 14, so I think it may have earlier very easy possible that you may have not explored this particular path. You know this particular point, that we are exploring from left to right, therefore we explored 14, 5 and 2, but if somehow we have explored the 2 first, then we may not have explored these 2 things. Pruning are better pruning as possible. So therefore there is a question, key order matters. Okay, question is order matters, that in which order you are going to proceed, and this order is not specified in this particular algorithm. This algorithm only talks about that how to what are the scenarios when you can prune the rest of the trees. So somehow we can find out that this is likely to be the best successor, it would be a better idea that you should go into that way. Are you with me? You understand this thing. The order matters. Are you with me? That order matters. Are you with me? No? Mail this. The order matters. Yes, sir. Okay. So order matters. So somehow I know that this is the best order, so I should go with that order. If this is best order, I should go by that. So it's possible to go in this way. So if somebody tells me that this is the better way, then I would go into that way. There is no for the perfect thing. If somebody tells me that this is the perfect way, somehow he can tell. Not use the search. Just use his understanding, because he knows that these are the best places. So why should I ponder around? He tell me that these are the best things, then I would follow that particular thing. I would use his things to give me a solution. So perfectly it is not possible, but some heuristics you can use by which we can improve. So obvious thing, we have seen that the best thing with the perfect ordering, we need to examine only m to the power half of the nodes. We have seen this. We have earlier seen this. This is not possible. We have just discussed that this is not possible, because if somebody has some perfect ordering, he has some understanding of the perfect ordering, then we can use that ordering to go ahead with the search. We would not even do the search. So perfect order is therefore not possible. Therefore, we should go for the other things. So what is the other way? Other way could be, whenever you are someplace, you take the random order. Okay, you go the random order. So when a place you take randomly out of 3 choices, you randomly pick something. Seems to be the something that takes b to the power 3 by 4 nodes. Okay, so set up that if you don't prune, you are going to spend b to the power m. Now you're pruning but you know the order, you are randomly picking the items to be seen, then it becomes b to the power m by 4. Okay, some you and this, is it clear? Then to the next slide. Next point. Is it slide more? Mark it clear? How 3 by 4 come. So let's not talk about this, but if you understand that there is 3 by 4, then I'm okay, because finding out this 3 by 4 actually need to do a derivation with respect to the random ordering, that I'm taking the things randomly, then what is going to happen, then I would do some proof and then I would come to this number. But you understand one thing, that initially if you don't do something, how many is required? Order of b to the power n. You cannot go perfectly, but if you go perfectly, somehow somebody can prove that this is the best way to go. And if some carefully selected example, carefully selected something, if you go by that way, then you will need to explode b to the power n by 2. But that's not available. That particular mechanism is not available. You can go for the random ordering. So you close your eyes, you just go for the random ordering, and if you go for the random ordering, you are going to take this much number of steps. That is better than the order b to the power, I think b to the power m. This is better than the b to the power m, but not that better, because the exponential, the exponential things grow fast. So if you make it 3 by 4, again, it's not that bad. But next strategy. Therefore, if you understand this, we want to talk about the next strategy. In chess strategy, if you want to follow this particular strategy, let's assume the game is chess and you follow this strategy. What is, whenever there is a possibility of capture, because there is possibilities. Sometimes you can capture something, you can put 3 to the other person, and you just forward your move and then take backward your move. Whatever you have done, you take the backward. These 3 things, you can capture something in front of you. Something is in front of you, you capture that. Some threat means you can provide some problems to the opponent. Then you go ahead to provide the problems. Means there is some ordering. So if there is a possibility of giving 3 and possibility of capture something, you would capture that particular item. If there is a possibility to just move something forward, and by there is something by which you can get a threat, so you would go for the third one. Similarly, you can take this some step back and there is some way of going forward, so you would go for the forward first. If you go with this ordering, it has turned out this that this much of things are only explode. Order to the power n by 2 items are actually explode, but now the cost factor is double. Means earlier whatever number of items you were exploring, this time double number of items are exploding, but same thing you are going to happen. So this is the second way, in random order, or you define some, you by yourself decide some strategy, and using that strategy, and this strategy, particularly this particular strategy, would give you a better solution in the case of chess. Sometimes this is also another a good idea, that you try first the moves that were found useful in the past. Useful means, you know that because you are playing multiple games, you know by the previous thing that okay, these moves were active, by this move I find out the better results. So there is some table is needed. So in those table you can find out the killer moves that can take you forward. You use that. This is another method. Okay. Sometimes this is also a better thing. The iterative deepening could help. So what is iterative deepening? Means if you want to see that one were forwarding, and you see that I would not go forward below this particular range, and what I want to make is that what I want to see is this, that let's assume that here, and somehow you have explored to this particular point and into history, and you here you want to find out what is the next move, and assume the next moves available are these 3-4 moves are available. So what is suggestion? Suggestion is this, that let's, because this tree is going to be infinite depth, you say that I'm not going to explore the tree. I'm going to explore the tree up to this particular depth, say this small depth. Okay, till this depth, you iterative deepening, you find out that what is the best way. Find out the best way, best place this. Okay, so how to reach from here? You find out this thing, this way. So this gives you that understanding that you should take this particular move. In the instead earlier what you were doing, just let me tell you, earlier what you were doing, you from here from this move, this to find out the best thing. If you go down completely, then you would be able to find out which is the best one. It is going to take a lot of time. This I'm telling, instead of going this complete depth, you just use iterative deepening. Deepening means you set by some depth. You say that I would only go to and search into this depth. I would find that which is the best one, and then I would forward into this direction. And really, if you come to the next state, here again you would be your iterative deepening would go further, because this time you have to go further, and one by one you are going. So in this way you can proceed. So this is the other way. So okay, iterative deepening could help add constant, because it have seen into the previous discussion also that it adds only constant action of the time. Time transposition table is a good thing to know. What is that actually? Sometimes whenever you are applying something, because in the game of chess you know that whenever you are playing the game you can take the things forward, backward, and sometimes what may happen that you can reach to the same location, same state that you were earlier in. So what may happen that in the you find out that this particular state and this particular state same. It may, because you both are moving, and some place you see that again we are under the same positions. So again, if you are into the same position, here again you have to search and find out which is the best one. So you can maintain a table, hash table, and in the hash table, whenever you are exploring a state, you are putting that, and you are putting what is the best value and how you take the move. At a later point of time, if you accidentally arrive at this place, it would take order of, the accessing of hash table takes only order of one time. So whenever you are here, you just try to see if this place is available for things, and therefore you can fasten your search. So this is also good strategy. So this is also a strategy that's able to previously seen positions we can read the computation in there. So we take a short break here, and we would start at 8. Any motions?